Good evening, everyone. So this is our first webinar that are going to start today. The objective of this webinar to discuss various topics in the field of digital system design, so that every students and research scholars may find these topics very useful. So today we are going to discuss the very important topic, that is implementation of low-pass filter and its application using field gate programmable array. Today, our speaker, Dr. Avik Kumar will present a short discussion on this topic. I hope that all of you will enjoy this topic. Thank you. Avik, you can start now.
Okay, thank you, Dr. Roy, for a kind and brief introduction. It's my pleasure to present the first, I'm honored to present the first lecture, short discussion on the digital system design platform. Before presenting, I want to thank Dr. Shishendu Roy for giving me this opportunity here. And so I'm beginning with the presentation. Is the screen visible?
I think it's visible.
Okay, thank you. Okay, good evening all the persons present here. I am Avik Kumar Das, a research scholar of IIT Shibpur in the Department of Electronics and Telecommunication Engineering. I'm here to discuss a brief lecture on realization and application of low pass filter using FPGA. So this is organized by the Digital System Design Platform, and I'm here now in Kolkata, India. So let's begin with the topic. So this is the brief outline of my presentation. How I have, in short time I have prepared it, and the whole discussion will be flowing in this way: introduction of low pass filter, following by the classification of the low pass filter, then the FIR low pass filter, IIR, followed by the application, then FIR and IIR filter, low pass filter design using FPGA, and then conclusion and future work. So moving on, low pass filter. So we all are very much aware about this filter term. So from this filter, I have chosen the low pass filter for the first presentation in the DSD platform. The low pass filter here, I have just a basic image of low pass filter, how I have chosen it. So these are the four type of filter I have present here: a high pass filter, band pass filter, the mix of the filter, among which the low pass filter always choose the lower frequency band to pass, the block the higher ones. So from these other filters, high pass, band pass, and the notch filters, exactly, that is a band stop filter, we'll be discussing in the next webinars. So moving on to the low pass filter, this is the basic block diagram. Actually I have prepared this total presentation for all the persons who will be watching this from starting from the scratch to the FPGA application. So here is the input and the output of the basic function diagram, where depending on this input, actually we can define the system. This is our transfer function of the system. Depending on the system input, that is, if it's impulse, so impulse response we will get in the output. If it's step, then we will get the step response in the output. So this is the transfer function of a filter. So now why it is low pass filter, I'll be discussing it. Then first we have basic things. The fundamental things is the differential equation generation. From this transfer function, I have derived this differential equation format for the next level of applications. And then we have the discretization of the low pass filter, because today's discussion will be mainly focusing on the digital aspect, digital portions. So discretization is very important. So here the transfer function which we have shown in the previous slides, you can see that from the Euler backward method we have defined the yk equals to 1 minus a, and that is k minus 1 plus a to uk, that is u is the input shown in this slide, and this yk minus 1 in the delete function, and a is denoted by this block ts by tf into ts, and ts is the sampling because discretization is going on here. And these are also the basic things. The transfer function actually I have mentioned here because for the low pass filter, how it is become a low pass filter, the transfer function is shown here. It is in the Fourier domain. Previous one I have discussed in the Laplace domain. So in the Fourier domain, in the transfer function we can see that if we sort it down, then it will be 1 by 1 plus RC j omega c. If we put the frequency omega equals to 0, then we'll get a higher value. It will come infinity, but that means it's higher. And if we put the omega equals to infinite, that is a huge value, then the transfer function will be tends to 0 like that. So that from this transfer function is satisfying the low pass filter. So for the reason I have put this two diagram for understanding the low pass filter. These are the actually passive components, and there's an order of the filter. But the order of the filter actually can relate it from this slide. Okay, I can in short, actually, for example, I can say that the order of the filter will be the reactive component measured by the reactive components, in short, of the filter. In the filter it is used the reactive components. Suppose the reactive components will be there is the C and the L and C. So in that case, that order will be 2 and 1. And the next slide, these are the basic applications of the low pass filter. First one, actually there are many applications of the low pass filter. This one is the brief. I've sorted down for the usefulness. The first one is the for it is used, you can see from the amplitude modulation to the communication model, that it's widely used in the communication circuits and systems for removing the high noisy signals. Then there is an application in the audio purpose, then the huge application in the biomedical purpose. Next, the audio loudspeaker, subwoofers, it's a sound system, etc. It's very important to remove the higher order noise items. Then the D2A converter, then also it is very much useful in the anti-aliasing filters, aliasing for removing the extra higher orders. And it is also useful in the wave analyzer, audio amplifier, etc. Moving on to the next slide, the classification of the filters. This is one of the hardest work I have to do, because we know that many kind of filters are there. Actually we cannot classify a filter or a low pass filter in a particular any domain. For the usefulness, I have put the 3 genre, actually sector of the classification, but it cannot be classified into fixed categories. So each and every filter will be in another filter subset. So like that, LPF can be categorized. There can be an active and passive low pass filter. There will be a active and passive analog and digital. As active and passive low pass filter, like that, analog and digital low pass filter will be also there. and there will be a FIR and IR. Obviously it is coming under the domain of the digital low pass filter, but it's used widely, so that I have categorized it in a different sector. So moving on to that, the active filter, these are the basic things we all know. It is active filter. You can just go through it in a very short way. It is active because the active element like op amp, register, op amp, sorry, not register, transistor, diode is present here. And in the passive filter there is no active element, only the passive element like resistance, capacitance is present here. So these are the basic two types of classification of the low pass filter. So I've just this is the chart, we all have gone through it in the UG syllabus, but in short I can mention that these first 3 points have mentioned about the effectiveness and of the passive filter, active filter, because in the first point it is mentioned that the integrating active components will help. The gain of the amplifier control by the feedback system, that the input doesn't go and experience the attenuation, and this cannot be achieved by the passive filters. This is also a thing, and so there's a op amp that actually helps. These things, 3 things are the active active for the active filters. It's a good thing, but the main drawback can say that the filter performance will be limited to the 500 kilohertz, but for the passive filters it will be a 500 megahertz, which is a big difference, which actually affect a lot for application. So passive filter, this point will be getting a huge applications field. And another point is that the active components are more sensible to the environmental factors. So if we are focusing on the electronic applications, so if we go for the passive components, then it will be very much environment friendly rather than the active elements. So for the although these 3 are the maybe the few drawbacks of the passive filters, but these 2 will be a huge advantage of the passive filters. So this is a chart, and next one I have this is actually I've written many things here, but the main objective of this is analog filter to digital filter journey. So this journey is important. First one is already I've said, the analog filters and op amp, inductor, capacitor is made of these things, and it's fairly simple but its complexity is higher little. But for the digital system, the first 3 or 4 points are how the journey has gone from analog to digital domain, but in the main thing come in the explain in the last point. The thing is that previously when the analog filters are used, for the real life applications, they are mainly the analog sensors as used. So when the research is going on the digital sensors, but it's not available in the market, from the analog sensors, analog data conversion to the digital domain, so really very hard. Yeah, although ADC is there, but nowadays using the digital filters is helping very much. So working with low pass filters using the digital sensors or the MCU, that is microprocessor, SoC, that is FPGA, obviously system on chip processors, will be helping a lot. That's the point. Next, that is the basic analog low pass filter. Designed it, the transistor and the capacitor resistance here. This is the low pass filter diagram, that it shows that it satisfies the low pass filter characteristics, but for the better view we can see that the frequency domain is giving the better view. The same thing is applied as the designed here, the digital domain, and you can see the same type of output is coming here. For the time domain, the impulse response, the time domain is here, and this is the frequency domain, and this is the digital domain, that's the inverse Z transform. This is the summer here, register is also here, and A is the gain here. Now moving on to the FIR and IIR filter, low pass filters. So FIR filter, from the name we can see that it's the finite impulse response, and IIR filter is the infinite impulse response. Both are the digital filters. The IIR filters are characterized by the fact they use the delayed version of the input signal and feedback and delayed versions of the output signal to the filter to input the to filter the input to the output. This is for the IIR filter, and for the FIR filter just a few differences there, and it is designed by finding the coefficient of the filter coefficient and the filter order that meet the certain specification, which can be in the time domain and or in the frequency domain. For the time domain example will be the matched filter. So just a difference for the plotting. This is I have presented. We all know these things, but the main point is for FIR filter, one thing is that feedback circuitry for this easy to implement. Implementation is very comparatively easy than IIR filter, but depending on the system and everything, these topics, these comparison topics, depending on the application, it can be varied actually. Suppose in the effective and sensitivity point, you can say that FIR filter is less computational efficient and less sensitive, and where IIR filter is more like that. And for the stability purpose, you can say that the FIR filters are more stable, as the present output doesn't hold any relationship with the previous output. For the IIR filter, it's comparatively less stable. And the memory, for the memory requirement, it requires more memory for the FIR filter, and for the IIR filter it's less memory it's required. So we have till now we have the journey from the type of filter: active, passive filter, analog digital filter, to FIR filter. So the journey in the DSP, the digital filters. So, yeah. Now FIR filters. So we have already discussed about it, and the main part is the equation, that is the how FIR filter is designed, is shown here. It's the finite impulse response filter. The impulse response is finite it is of finite impulse duration, because it settles to 0 in the finite time, so that it's finite. FIR, finite impulse response. You can see from the equation that the yn equals to the summation k equals to 0 to m minus 1 m, that is the length the sequence, and you can get the finally the yn equals to summation k equals to 0 to m minus 1 and hk x of n minus k, that is the delay unit. The k amount of delay is happening time to time, so this point is implemented here, the delay unit. You can see that xn is given fitted here and the delay unit is here, and then the gradually delay is occurring, and in every delay the summing point that is added up to here for the getting the total final out. And FIR filter design methods. Now there are the 4 basic and important methods for designing the FIR filter, that is Fourier transform method, and then one is the window transform method. So frequency sampling method is also here, and another one is Park-MacLean algorithm. I didn't mention and explain all these things here, because this explanation and presentation of this each and every methods is a lengthy process, and it will take time. So these are the methods of designing the FIR filters. This is a form 1 I think I have taken just for the example purpose, low pass filter, where xk, this is the input and this is the output side, and that by time to time delay the gain is summed up here. Just one thing, thank you, mention that for implementation of the FIR filter, Z inverse, that is the register, you can use for the implementation of FPGA, that is a register here, and this is the multiplier, the term of FPGA, and summary is the adder here. So this is the from the presentation we can link with the FPGA. So from here, this is the actually presentation of the model, and this is a simulation result actually with using Matlab for the FIR filter response. You can see that the response is giving the low pass filter output, and in case of Matlab simulation, there is also already a tool and library is also there. So in Matlab we can easily simulate this FIR and IR kind of filters. So this is the result, and next one is the IIR filter, and this is the infinite impulse response filter. Is so from the name you can see that it's infinite impulse response, not like the finite response. It's a recursive filter in that the output from the filter is computed by using the current and previous inputs, current input and previous output. So here you can see that in the FIR filter there is no feedback system, where in the IIR filter you can see that there is the feedback operation, so which makes a lot of difference with this FIR and IIR filter realization and application and output generation. So the difference equation is like that: yn equals to summation I equals to 0 to n ai, that is n x n minus I, plus summation j equals to 1 to n, and that is bj y n minus j. N is the filters order, which I have already previously discussed that order. And finally the transfer function is coming hz, that is summation I equals to 0 to n ai z power minus 1 plus divided by 1 plus summation j equals to 1 to n bj z power minus 1. So that's the transfer function. And then these are the IIR filter design methods. So from the first one is the I've written the bilinear transformation method, that is BLT. Next one is the impulse variant design, and next one is the pole zero placement design. So like the previous FIR filter design methods, I've just only mentioned the different design methods and techniques. After in the next webinars presentation it will be discussed. And these are the three IIR filter, low pass filter, IIR low pass filter Matlab simulations are presented. First one is the Barter-Rot filters output, next one is the Chebyshev type 2 filters output, and next one is the Bessel's filters using output. You can see that all the filters are showing the low pass filter outputs, but there is a slightly difference between each and every filter applications. These are all done using Matlab, and the code is available. You can use it and run your code. So it actually depending on the applications, you will use the exact filter. Filter means which type of design method you want to apply for IIR LPF. And next one is the application of the low pass filter. So here what I discussed in the previously, so also notes like that there's in the DSP domain, the low pass filter is to remove the spikes of the curve. A is the high frequency components and the denoising of the audio. So we can understand that what is actually high. Actually everything that high frequency domain is removed, and it's being smooth, making smooth, or making smoother output, low pass filter is implemented. The Barter-Rot and Chebyshev filter, this output is shown here, and this is the output of the Matlab, not Matlab simulations, just the output shown here. And next actually I have application. Previously I told it just the fields, but these are the application using specific application, the specific fields, the low pass filter in the which specific fields it is applied. First one is the DSP, this application. Next one is the IoT. This is the recent paper I have surveyed. This paper of 2020 papers. The name is the integrated CMOS active low pass filter for IoT, where the low pass filter is considered as the low pass filter is considered as a very sustainable block It suppresses the every type of undesirable signals and noise. So in this IoT application for of RFID, this low pass filters plays an important role. This is a block diagram where the antenna is antenna and the band pass filter actually it is used here, and the low noise amplifier is here. This is the receiver part and this is the transmitter part and this is the connection, where this paper actually explains. I have put the paper's name in the reference. Use the low pass filter beautifully in the IoT application. Next one is the application and use of low pass filter in the image processing. So image processing is a very important domain of the signal processing. So in the image processing, you can see that the outputs, from the outputs you can see that the three Gaussian low pass filter, one is Barter-Rot low pass filter and another one is ideal low pass filter is implemented for making the changes in the low pass filter. So here in the low pass filtering, Aka smoothing is employed for removing the high tail domain noise and from a digital image. And the low pass filter usually employ moving a window operator which affects 1 pixel of the image at a time, changing the value of the sum function and the local region. Actually windowing method, the pixel, it changes this kind of thing actually affect by using the low pass filter, where the high value of the pixels are removed. So this is one of the very useful application of low pass filter in case of image processing. Now there is the actually comparison for the low pass filter. It is not actually, it is a generalized comparison where ASIC, DSP and FPGA, the performance, cost, power, flexibility and design effort are plotted with the 4 types of general purpose processor, reconfigurable processor hardware, that is FPGA, along with the programmable DSP and ASIC. So you can see that if we consider all these heads, all these parameters, then FPGA is always providing a very efficient and very good application for the a comparison with the other 3. From this, the advantage, what is the advantage then of the FPGA in the DSP application? Because what we have previously seen is the DSP application, in here FIR and IIR filters, all the digital signal processing filters. So in this case, if we compare, the FPGA has more as it process parallelly, so FPGA's output is more than the DSP processor, and it is also the low cost for the multi-channel applications where DSP processor are not, and is obviously the hardware is flexible and implementation is very flexible for the FPGA because you can configure it using Xilinx or other tools, Vivado. And next one is single chip solution is always, FPGA is always provided it for. This one I have just previously gone through this slide. This is actually how the direct from 1 or 2 whatever we apply for IIR or FIR filter, this block, actually this is the register block, this is the Z inverter, the Z transform, and this is a multiplier and adder, such that we consider it, write a code on Xilinx and using these block diagrams, and then this shows the output. After that means it's born the hardware FPGA. And this is the useful resources and future research areas of the low pass filters. Actually in the survey we have seen that this is the analog devices. It's actually online platform they have designed, where you can, I'll be showing it this slide, where we can actually design, we can put the limit value with the cutoff frequency of the filter, and we can design what type of filter we are providing. Actually this is this website, what it has done, actually gathered all the types of filter and they have compiled it all together. So you can also do this by yourself in home, but it's actually very useful. Next one is the I have gone through this DSD digital system design page, and seen that the pipeline implementation of the IIR low pass filter, it's beautifully executed in that website. I have gone through that. The realization and the FPGA code is perfect. It's working nicely. The next one is the more general and non-linear optimization. That optimization can of course be used to meet the more general frequency and or the time domain parameters. Obviously optimization for the non-linear systems will work, because we here two things I didn't mention: the time invariant LTI system and time variant system. On the time variant system, implementation of low pass filter is really challenging for considering its samples. Time variant, it's really in research work is going on this in that domain. So I mentioned it in the next point. The design of time variant LPF system is very really challenging actually. And these are the references, and that's it. Till now, in short time I managed these things here. That's it. Thank you.
Thank you, Avik, for presenting a nice description of low pass filter and its applications.